is they produce their own energy every day using biomass. And the biomass எப்படின்னா you get இந்த பாம் ஆயில் சீட்ஸ் வந்து அதுல வந்து நார் வரும். நாருங்கிறது இந்த ஃபைபர்ஸ். அந்த ஃபைபரை எடுத்து இந்த கோகோனட் ஃபைபர் இருக்கு இல்லையா, நம்ம கோகோனட்ல வந்து இந்த நார் இருக்கும். அந்த கோகோனட் ஃபைபரை எடுத்து அதை வந்து ப்ரிசர்வ் பண்ணி then they use like 4,000 tons a day to produce electricity. So they are self-sustaining. They're not depending on grid. So completely 100% their own renewable sources. That's a fantastic, impressive concept they have developed. So people can do that kind of technology. Then similarly, so we need to see how we can reinvent and regenerate. There is always a scope for that. Clean up water. Science tells us next decade is crucial for us to undo the catastrophe and turn back the tide to pollution and end the special laws. So now I have given you the massive problems. Okay, these are all massive, big challenges. How do we do this? Why I need to choose academics is like, I always believe in socially oriented transformation research that has direct benefit to society. Of course, we need to publish papers, which we have been doing. Papers in the sense that sharing the knowledge itself is a paper, communicated. So the communication which we are doing, that will also directly benefit society. But beyond that, publish, we need to produce our products, and we need to produce PhD students to be a socially responsible citizen who can transfer their knowledge to others. How do we do that? That is what I like to do in the next 15-20 minutes or 30 minutes. Okay, so we are working on a concept. I really explained that in the first slide, energy water nexus. I mean, I have told that is where we are focusing on how surface engineering of materials will make them products much more smoother, cleaner, and also effective. So we are working on cutting edge research materials. Bear in mind, these are all earth abundant materials. Okay, the manufacturing of functional materials for energy storage and harvesting, 3D printing and additive manufacturing, and plasma-based processes, which is something like this, which I will touch with this, sensor technology, smart materials for coatings, and smart buildings. Okay, so it is pretty much like, I think presumably most of them are physics students. So you know what is a plasma, ionized gas. So on the ionized gas, I will show you, I will discuss this. So research is sustainable. So there are a lot. I don't work on solos. I don't believe working on my own. I collaborate really a lot. That's the reason why I feel that not everyone can do everything. We have to make sure that there is always a diversity, and also working togetherness brings different changes. So we work on, my group work on quality education, clean water and sanitation, and clean energy. This is the 3 SDGs we work together. And quite a lot of funders work quite a lot with India. UKering program fund பண்ணிருக்காங்க. In fact, actually I have got 3 projects with UKering. In fact, last week then Newton Fund, Royal Society, British Council. There are lots of good funders out there because we have some ideas. Our ongoing projects on waste to freshing or the wastewater treatment related. So that is on about 8.5 million. Recycling of batteries. அது பண்ணிட்டு இருக்கோம். செல்ஃப் கிளீனிங் ஆஃப் சோலார் செல்ஸ் ஓட ஹவு சோலார் இப்போ வந்து நம்ம we have massive deployment of solar cells in India. And what happens when you started accumulating dusts, so you are putting water and clean it, or put soap and clean it, but there is a layer of dust which doesn't go. Why it doesn't go, why it's not going out? That's pure surface chemistry. I think somebody in the morning started presenting about hydrophobicity and the marla. So we are doing a super hydrophobic coating, transparent super hydrophobic coating on the solar cells to make sure that this particular solar cells is or water poured over splash kilo vandrum. So that is a project which we funded, and then different recycling methods. So there are several projects are there. How do all these projects tie together? So if you look at this, you need to have 2 types of research. One is producing materials That is preparation of materials, other is characterization and devices. So if you look at this, we focus particularly on plasma processing of materials, and then different types of evaporation, electrochemical methods, including metal oxides, and then semiconductors, from graphene, and then new 2D materials, maxine, work பண்ணிட்டு then have an excellent characterization which we are doing. And I think, in fact, we also do some characterization with your group in Palangote. I think Dr. Baby Mariata, I think she has sent some samples, so we will be characterizing that for her, and we are happy to support them. And I always believe in collaboration. That's why I have people from IIT Delhi to many other collaborators, including Cambridge, etc. And then we work very closely with industries. These are all live industry projects. நிறைய ப்ராஜெக்ட்ஸ் போட்டுட்டு இருந்தேன். எனர்ஜி, என்வாயர்மெண்ட் அண்ட் இண்டஸ்ட்ரியல் இனோவேஷன் இஸ் கீ. அண்ட் ஐ வுட் கிவ் சம் எக்ஸாம்பிள்ஸ். அண்ட் ஒன் ஆஃப் த எக்ஸாம்பிள்ஸ் இஸ் வேஸ்ட் வாட்டர் மேனேஜ்மெண்ட் using our technology. So this is not a cartoon picture. There's no graphics attached to this. This is a real picture coming out of this building. Okay, this is the textile building. They produce masses of textiles, and look at this untreated water they are putting directly into the thing. Not far from us, Bangladesh. So we thought that we have to attack this problem, and we put a proposal to Royal Academy of Engineering together with other colleagues. And then because I believe in interdisciplinarity, so now on the materials treatment, whereas I thought that I always keen to work with my motivation is work with skills development with the people who does not have access to the high-end technologies. So I choose PSG College of Technology. We was grateful that they were able to participate, so that we can have a biotechnology, bioremediation along with physics. This is very important concepts, anaerobic and aerobic digestion initiative. Then how we can do this anaerobic aerobic digestion initiative. Then also using material physics, how we can treat both biological and physical processes to the clean water. And we have also chosen a partner, Watson Environ Technology company, very small scale company, how we can do a field test with them being a project. So we did some good conferences and studies about that, both in UK and India, inviting industries, what are all the industry challenges. Then we nailed down the problem further. So India is one of the major textile sector and exporter of 60 billion in 2019. It could be even more now. And textile industry consumes 140 liters of water per kg. Per kg, 1 kg 140 liters of water. Fresh water, not recycled water. They don't recycle the water again. Fresh water they used. Dyeing is one of the most polluting chain of activities. Wastewater plant processes challenges due to lack of efficient economical way to reduce organic contaminants. And these could be the carcinogenic components, and some unconfirmed reports saying that people in particular region even loses the male fertility. So there are lots of challenges. We were glad to visit some of the industry sites where they do the wastewater. We made some suggestions. And who are all these guys using is Marks and Spencer, Macy's, and money country. Water is not a new challenge. It is there for years. Okay, in the 4000 BCs, ancient Greeks and Indians, including Indians, we treat water using charcoal filtration. It's one of the best filtration known until now. Use the sunlight and the boiling and strain to improve the taste and color. அதுக்கப்புறம் ஈஜிப்சியன்ஸ் என்ன பண்ணாங்க, ஈஜிப்சியன்ஸ் ஆலம் போட்டாங்க. நம்ம ஊர்லலாம் நம்ம வீட்டில் சொல்லுவோமே ஆலம்ல போட்டு குடிக்கணும் அப்படிம்பாங்க. ஸோ ஐ யூஸ்ட் ஆலம் டு காஸ் சஸ்பெண்டட் பார்ட்டிகல்ஸ். இந்த இடத்துல பார்த்தீங்கன்னா கொஞ்சம் பெருசாக தெரியும். இந்த இடத்துல சஸ்பெண்டட் பார்ட்டிகல்ஸ் ஆர் தீஸ் ஆர் நானோ பார்ட்டிகல்ஸ் ஆக்சுவலி. And then they pressurize and pump the water so that the suspended particles settle at the bottom, and then you get a clean water. அதுக்கப்புறம் the filtration used widely. Then after that we saw identification of waterborne diseases, cholera அப்புறம் pathogens we started looking at, and then advancement to industrial sector, using man-made chemicals, VOCs, volatile organic compounds, etc. So it is progressed like anything. Then we started about then the government started getting into Clean Water Act, safe drinking water, reverse osmosis. In fact, reverse osmosis was one of the worst product ever discovered, because the reverse osmosis takes away all the minerals out of the water and giving you nothing. Nothing in the sense zero. The stay, it is like all the minerals. It's like pretty much you are drinking your water. That's not healthier to younger generation at all. We lose all the minerals, vitamins, and proteins in the water. So I don't know, actually. It is a technology which I will never recommend to anyone. So let us focus on water and sun. Water shortage and energy crisis are the two most global challenges which we know. Energy and water. ரெண்டுமே இல்லைன்னா the பூலோகமே இயங்காது. The solution to this crisis are based on sustainable energy sources. Can we use solar-inspired water purification? It is an efficient green energy sources. How do we do that together with microbial and antimicrobial treatments? And the photocatalytic degradation is an important method for water purification, okay, by the virtue of advanced oxidation process. And AOP is used to, we can use this to reduce the toxic components by producing hydroxyl radicals. Okay, so I will show you, and we can use both the solar energy spectrum. Solar energy spectrum consists of both UV and IR, and it consists of how we can use the visible light spectrum, so that we use the natural sunlight to reduce the organic contaminants present in the effluents of wastewater, which I explained to you before. So in this talk, I will focus on 2D materials such as molybdenum sulfide, graphene, maxine, and plasma deposition of this. So for the benefit of undergraduate students, I haven't prepared the slide. So graphene, it's a what do you call? It won Nobel Prize for its innovation. So it is nothing but now one of the million of people who does not realize the importance of research. Is when I was doing 2000 in my PhDs, 2001 to 2004, graphite pencil that is what is graphite is. Lead based. Lead it came from Greek word. Okay, but it is not lead actually. It is a graphite. And the graphite when I was working on surface science to understand the properties of graphite, we completely cleave it and flat. We roll it with cellophane tape and cleave the graphite and part of shiny material. We don't even realize what is the shiny material. We put that in the bin and then make the graphite flat, and then we do the deposition. So that thing which is shiny, which we put in the bin, that was discovered to be a graphene and lightest and thinnest material. Okay, so I am one of those million stupid people who forgot to do the proper science. In the same thing, the reason why I shared this story is, do not, when you are doing research or when you study something, do not leave anything, even if junka. I think you need to focus and see there could be some problem which you can address, or some learnings are that which will take you to longer way. So once graphene discovered, there are many millions of materials started coming out, two-dimensional materials. Okay, so single dimension, one dimension, two dimension, and three dimensions. So means that the activity, the properties will be on only one directions, and the two directions and three dimensions having a x, y, z directions. So this is confinement. We have to call that as a quantum confinement. So probably as a physicist, you may be knowing what is quantum confinement, etc. So how we can use this technology to address this? So we use solar as a wide band gap, because wide band gap you can see from IR to visible light to infrared, wide band gap. So how we can The advantage of using material science, the advantage of using material science is can each and every material can be tuned in such a way that it can attack the specific properties. So right from borofin to molybdenum sulfide, it's all two-dimensional structure. It's like a planar structures. These planar structures, then how we can functionalize this to change the band gap to tune to the particular effluent or particular organics to reduce the organics. Okay, and this can be used using photo-induced antimicrobial activities, and then photothermal evaporation, and finally photo degradation activities. So where you shine light and then you produce excitons. Excitons the electron hole pair. Okay, so you shine light and kick the electron out of the surface. Okay, and this forms a hole, core hole. And this core hole, and the electron is just going into the unoccupied density of states and forming a pair, electron hole pair. And this pair can rotate and finally quench. Okay, releasing light. And that is where that is important in reducing the organic radicals or pollutants, and then that degrades the dye. Okay, and 2D systems are generally like single layer graphene to multi-layer graphene. Multi-layer more than 2 or 3, multi-layer including graphene oxide. You can have an oxides of graphene. If you have any questions, you can stop me at any time, and then I'm happy to explain. And then TMD, it's a very important family of materials. One of them is molybdenum sulfide, there's tungsten sulfide, etc. There is newly developed one is Maxine. They're like a burger mari. So you can have a different types of integrated materials, like molybdenum sulfide, graphene, and then Maxine, and then you can repeat the structures. So it will show that you are catering the whole wavelength of light. Okay, what are all the applications? Many applications: photocatalysis, batteries, perovskite solar cells, sensors. You can name it, you can have it. Okay, why need 2D materials? These are all degradation and purification due to their large surface. Nanomaterials, it has a large surface area. A pretty large surface area, I can put, if I take a football, I cannot put a football in a tumbler. But if I slice those footballs into smaller balls, I can put it in the tumbler. All the football, I can put it inside the tumbler. The reason is the surface area is increased when I started putting small. The same quantity can go inside. Very simple concept. You can go into atomic physics, molecular physics, and talk about quantum confinements and how the size of the particle changes. That's not an issue at all. Okay, then large broad band gap, engineering the band gap to form the electron hole pair under the light, both in terms of visible light and also ultraviolet. You need to have a strong absorption its characteristics. So because when you start putting the light, it has to absorb at the particular wavelength so that the dyes are getting absorbed on the surface. When it gets absorbed means when there is a high electron hole pairs are there, then it gets absorbed on the surfaces. And these strong are due to electronic properties. Efficient photothermal and photocatalytic. Photo means light. We use light for catalysis. Catalysis is, we all know what is catalysis is. It speeds up the reactions. More active sites. So when you have nanoparticles, more surface area gives more active radicals. And different 2D materials can respond to different wavelengths. So TMDs or TMCs is transition metal chalcogenides. So excellent optical. So optical, we have to see really well. So the UV visible light and the properties, electrical properties, and then electrical and electronic properties. That means that I can tune this accordingly. Chemically and mechanical properties. Chemical properties means the dopant, how the dopant changes the properties of the system. So science simple concept dopant explain I think because of the undergraduate students are there, I just wanted to share some colloquially, but there is a lot of science in it as well. Right? It is very simple. making a rasam with parupu and pundu. Pundu is effectively a dopant in the rasam. You dope pundu. That is garlic, and then with garlic and without garlic, the taste different. The taste different because the structural and chemicals goes inside is different. It is the same thing. The chemical which we dope inside the layers, this goes and absorbs the light. And this absorption goes into a different transport phenomena. And this transport phenomena induces the molecular vibrations inside the chemical constituents that releases different higher, that releases stronger energy to break the hydroxide bonds. That is where the chalcogenides are important in terms of its molecular structure, the TMD structures. Okay, that's important. That two outer layer of chalcogen atoms and one interlayer metal atoms, it holds the higher mechanical properties in bringing together. Okay, that's why 2D mass 2 is a classical example, along with TiO2. Titania is a very common material that is used in many applications. Including our tooth to face creams, then the 3D layered structures, stronger absorption. So in case of photocatalysis, being a physics lecture, I cannot leave without explaining the photocatalysis. So photocatalysis used in massive active sites to produce added absorption points for the photocatalytic reaction sites. Okay, and in terms of redox reactions between the reactants, photo-generated holes and electron need to satisfy the conditions. In the conditions, negative potential at the conduction band, at the bottom of the photocatalytic material lower than the reduction potential, and the positive potential at the valence band maximum. So if you take the band structures, band structure pretty much like my hand. So this is was a valence band, conduction band, there is a band gap. So when you take that, we need to focus on the top of the valence band and the bottom of the conduction band. So when you put the electron, particularly like this, you shine light, you pump the electrons there, and then you can have a co-catalyst, metal co-catalyst. Molybdenum sulfide, in our example, will take some co-catalyst with TiO2. So TiO2 acts as a main photocatalytic material. It forms an electron hole pair, and the co-catalyst will help to speed up those, pump those electrons into metals, and then they are asking as a resonant particles, like pretty much like how you do the drums. Drums are with a beat pannumbodhu, imagine the stick acts as a metal catalyst and the drum acts as a TiO2, so that the energy is transferred. Okay, and that will forms a composites, and that composites work with the electronic absorption of the catalyst. In our work, we work on different materials, like the TiO2, where we shine light, and then forming the electron hole pair, and we have an advanced oxidation process and reduction process takes place, and we release water, organic pollutants, and the hydrogen oxide. Hydrogen oxide. It is hydrogen oxide is water, H2O. Okay, and see the difference where I told you about chemical treatment. So this is pristine TiO2. When we hydrogenate TiO2, there is a change in the optical properties. I can see clearly visually here. And then we started putting nanoparticles and metal atoms as a co-catalyst. In our case, it is silver. And then we can tune the metal properties. So this is the difference between the different treated, and you can clearly see the absorption. I told you about absorption. Either on the TiO2, and then we can change the wavelength by changing the different foreign atoms to put inside the TiO2. You can clearly see the changes in the wavelength, and this corresponds to different treatment of hydrogen as a photocatalysis, dye degradation. Okay, and then we started putting defects induced. So this is a transmission electron microscope of TiO2 along with silver nanoparticles. You can clearly see the difference of lattice spacing. X-ray diffraction எல்லாம் பார்த்திருப்பீங்கல்ல, ஒரு curve போடுவாங்க. The diffraction will use different fringes, and whereas நம்ம வந்து X-ray diffraction we cannot see visually, we will see the spectrum, but in transmission microscope we can clearly see. This is in my lab which we took, and then we can start thinking about shifting, the chemical shifting, and the chemical shift is the one which is pretty much like I gave a crude example of between Poondu rasam and normal rasam. The same thing here. When I induce, there is a chemical composition changes. That's why the chemical shift is happening. And this chemical shift is responsible for that absorption of light. And we do the fingerprint experiments of electron, X-ray photoelectron spectroscopy, X-ray photoelectron. So we use X-rays, photo, it acts as a photons, light, spectroscopy. So we use light to understand the chemical bond. நான் சொன்ன முன்னாடியே என்னோட ஸ்லைட்ல chemical bond அது வந்து plays a major role in understanding the properties of the system. So here in the left we have a titanium 2p. Okay, titanium 2p ங்கிறது வந்து 2p orbitals. Okay, one has 2p orbitals. So we probe in the 2p 3/2 1/2 and 3/2 of orbitals. அதில் வந்து என்னென்ன நடக்குது அப்படின்னு பார்த்தீங்கன்னா, அது வந்து this is called a line shape of the spectrum, and this line shape is very determines how the bell curveங்கிறது வந்து இந்த மாதிரி bell curve. So இது வந்து என்ன ஆகுதுன்னா, absorption, the photo absorption is taking place in the surface, and then the electrons are released and we collect the released electrons. அப்போ என்ன ஆகும்னா, these energy electrons goes and inelastic. So you have a scattering of electrons collect பண்றோம். அப்போ collect பண்ணும்போது in the doped and unsamples samples, you can see the doped sample in terms of hydrogen. You can new peak. This is nothing but titania 3p. So this is very research, or you need to be focusing on small things. Look at this. இதை வந்து நான் வந்து நார்மலா உங்ககிட்ட கொடுத்தேன்னா, you will not find anything. சார் எதுவுமே இல்லை அப்படிம்பீங்க. There's nothing there. But if you look at more in depth, this small peak makes such a big difference in the activity of the system. That is titania 3+. This titania 3+ is responsible for the photocatalytic activity. Okay, அது இல்லைன்னா catalytic activity இருக்காது. அதை வந்து நாங்கள் வந்து திருப்பியும் டைட்டானியாவை படுத்துட்டு then oxygen spectrum. So oxygen spectrumல பார்த்தீங்கன்னா, between the left and right there is a difference in the hydroxyl radicals. This hydroxyl radicals helps to reduce the chemicals. Okay, so once we produce all these in the small scale, lab scale, I always say that when you produce the lab scale, understand we have to make the system reproducible in a bigger scale so that the energy technology can be realized. So அப்போ வந்து நாங்க வந்து okay, this is not working, so probably I need to go to different pointer. Take out the laser. Yeah, so we scaled it up. Using our plasma printing methodology. பார்த்தீங்கன்னா, ஒரு இது வந்து homemade device. It's a cheap device. You can clearly see the plasma here. Plasma is ionized gases. We make some inks, and then the ink is now directly deposited onto any wafers or any substrates. We can do that. So that is what we are showing is a homemade system where we were able to use an additive manufacturing tool. So, and you can clearly see that we can draw lines, we can put contacts, etc. You can play with it. Okay, so then we started making materials, and you can clearly see in this video we are able to reduce the dyes using our technology by normal solar light. This one is mimicking solar lamp. Okay, and now here you can see these bubbles are going nicely out. There is nothing but hydrogen. It is releasing hydrogen into the atmosphere. So hydrogen, it's because from this waste dye water, we are able to get energy out of it. That is called waste to energy. Okay, then silver nanoparticles, these are all different. Size of the silver makes a difference. Then why TiO2 mass 2, different types of band gap, already I explained to you. So we make this process simple using a chemical treatment, hydrothermal treatment. Hydro is the water, thermal is the heat. So we mix water with and produce with heat, makes a composites, and the composites of which we will get a layer. Look how nicely it forms a layer. It's a very simple method of producing. And then different morphologies from flowers to lines, you can tune accordingly. These are all published data. And the XPS fingerprinting, we started characterizing this with the chemical sheets. And similarly, the XRD, which then we can start doing the band gap alignment. And then we started doing the optical absorption. This is a very important result. You can see that between the TiO2 to the molybdenum doped samples, there's a huge shift. This shift is tuning of band gap. Once you tune the band gap, then we started doping with different percentage from 2.5% to 50% of molybdenum sulfide. So we thought that 2.5% gives a really good photocatalytic activity, whereas 50% gives a lot of absorption. So why can't we use as a two-stage system? அப்படிங்கிறது பார்த்தீங்கன்னா இங்க வந்து நல்ல absorption வருது. And then this is the dark condition and the light conditions. You can clearly see it's flattening out. Then we thought that why can't we use the same material for photo absorption and degradation? Okay, in the process la pannadala, so we mix the pollutants, not only one pollutant, ella pollutant mix pannite. How this happens? I mean, two stage. So 50% acts as an absorption, it will residual dye on the one, then 2.5% ulla potu photo degradation panni we treat the water. Okay, and that is how it is. So we have pink color gets reduced to gray color in 50 minutes. But this is now our recent advances, we can do it in 5 minutes itself. And then the integration happens. Then you can clearly see that 0%. So we are going into good 0% with our material. And conclusion is the ultra thin 2D systems can do this by different cationic and anionic removal. Proof of concept is developed and installed. And I just wanted to quickly show the concepts of different electrolysis. So this is a industry wastewater dye, denim dyes, and then we treat it. You can clearly see the clean water here. Also sedimentation is there. It's called flocation, so which we already removed. This is an industry wastewater dye from Turkey. There is a denim factory. Then we started thinking that if we can mix it with salt water, that is available sodium, can we produce hydrogen from this using a simple copper electrode systems? And you can clearly see that this dye is constantly the catalytic process in the copper we coated some new materials, and you can clearly see that there is a bubble formation is happening. This bubble formation is nothing but hydrogen coming out of industry dye water. And you can see that we are using solar cells directly use to heat up. Now we are not going to use any other electrical systems. So we are using energy from solar energy to deliver solar energy to use solar energy, use as an electrical conductor to drive this. Okay, and then different effluents we are using that method. And then similarly we thought that different plasma sterilization plasma ionized gas. So we made a homemade system with the copper electrodes and shine plasma onto the dye. Now 50 minutes 30 minutes 30 minutes later we can clean the dye with some physical processes. And then in terms of biodegradation, so we used when we worked with PSG la vetiver na the thanniila munadila palaya kaathala vetiver thanni ulla potutu then they take the wear out or wear ullaye irukum, then you use that water to drink. That is a fantastic concept. It takes out microorganisms, it takes out of heavy metals, etc. from the system. So we have to go back to the technology where we reinvent it. So when the lots of, instead of RO water, I will even recommend vetiver at any time. So same concept we used. We went into the plant in Tirupur, in the dye in the plant. We use photocatalysis, and also on top of that vetiver to reduce the dyes directly into the different. So this is the COD and BOD. There is a chemical oxygen demand. Oxygen. Also, we did some really good treatment. So I think I have also close to 50 minutes, and we use natural products, nanofibers, to treat this water. We progressed in much further for biological treatment. Natural fibers, we extract these natural fibers, inject nanomaterials on it, and makes the biocomposites like vetiver. And then we use different bubble technologies, so even sensors, and finally hydrophobic systems. My team now, this team has grown up. I am the group leader of this team, and we are these some of the professors works with me, and we have a diverse kind of students from Brazil to Ghana to India, and now I'm having some Iranian. So we have received a good award for from the Theresa May and Narendra Modi for our work on UKD projects. And thanks very much. Before I close it, I wanted to tell one more thing. I talked about high-end research, but also high-end teaching is also important. So what we did is we made a remote solar lab. The solar cell vechite, people will say that solar cells will give energy. So why it is coming? How we can measure? How we can quantify this? How this education can be transferred? Everybody can, the world can learn this. And we made a office or a roof. So there is a pyranometer. Pyranometer measures the radiation of the light. Then solar cells, which we shine light onto them. These solar cells, and then anybody in the world can read the IV characteristics, current voltage characteristics, depending on this. Inclined, you can also rotate it. Okay, and new innovation shade shade artificial cloud cover. They can measure the irradiance, IV curves, power curves. There are many things you can do. Okay, this is another camera. We can do the experiments with the tilt angle, as I mentioned. So either Kota, Rajasthan, we had a project. We was doing the demonstration there. Okay, we can do the power characteristics. So these are all like science and technology can innovate. Okay, so with this, I would like to stop. I think I have loads to cover, but I thought that I leave it. And if you have any question, this is a new material, Maxine. This is a Maxine sample, which we have produced, and then we studied the electronic properties and the experimental play, etc. So always things that, thank you so much for listening. And I always believe everything starts from commitment. If you are committed to things, commit. And the commit and word name on the word. Commit to what we are doing, irrespective of whatever happens around you. Put the time. When you start putting the commitment and time, training will come automatically, because your mind is tuned into that. Yeah, it is. Then if you put if you put commitment and time, training comes automatically to you, and you will seeker of knowledge. So we are all seekers. Okay, we are seekers of knowledge. That seekness will give you training, and then great science and innovation starts. So it's a step. We cannot go into this straight away without having this. Okay, then the enthusiasm, with your enthusiasm, energies, and professional maturity, success will come. But success, for me, is success itself is when you start putting commitment. That itself is a success. And I wish you really all the best for your future endeavors. And in between but mostly English, but I would like to communicate in Tamil as well, so because so I'm pretty sure very little people will be seeing with English. So many thanks, and I have 10 minutes to take some questions, and thank you so much.
Dear participants, this invited talk is open for discussion. If you don't have any questions, you can raise the first person. At time, 2 questions. afternoon, sir. Dr. Sadish Kishimoji, this is the third time you are giving the talk during this pandemic. First time we were witnessing your lecture on COVID with the 3 doctors or 4 doctors, I think so. That was the first experience for me. But so, doctor, I'm just going to lay from the Department of Botany. Can you hear me? Am I audible to you, sir?
Yeah, கொஞ்சம் எனக்கு I'm not able to hear. It's a bit jarring. கொஞ்சம் mic கொஞ்சம் தள்ளி வச்சு பேசுனீங்கன்னா கேட்கும்னு நினைக்கிறேன். A bit closer, please. No, I'm not able to hear you, sir.
So thank you very much for your wonderful presentation.
Yeah, I can hear you now.
This is the third time that we will your lecture. Actually, this is the third time for me because before that already I attended 2 more talks on pandemic or COVID on different occasions. But as the surveying, this is the first time. Sorry, it's academically or very particularly on this. As a physics department organizing this wonderful talk on material science or its application, emerging materials or its applications. So as a biologist, basically you are a medical doctor. Could you suggest, because as you have mentioned one of the slides in which you have shown that textile treatment in Bangladesh, I think so. If I not correct, please refer the slides which you have shown us. Textile treatment. Am I audible to you, sir?
Yeah, textile treatment I can hear, yeah.
In Bangladesh, you have shown on our slides. So could you tell us or could you explain the bioirradiation, the role of bioirradiation on this crucial problem across the country, very particularly in India, very particularly through.
Yeah. So in the terms of textile effluents, so what happens is like people we work. People produce results using methylene blue as a dye. Adha vandu reduce pannittu. It's a good start for that, for the dye molecule. But if you go into the textile manufacturing plant, the textile manufacturing plant is a mix of dyes, very heavy dyes. And these heavy dyes, you cannot reduce it using just normal methods. So we need to have a biodegradable dyes, membranes. That membranes is what vetiver gives. So we use vetiver to absorb the initial on the photocatalysis. Photo is light. We need the catalysis to you have the light to penetrate inside. If you have a thicker dyes, it's very difficult for the light to penetrate inside. So in order to thin it down, the color, we use natural fibers. The vetiver natural fiber or even we have gone beyond vetiver also. Now we are using different nanocomposites, natural fibers. That natural fibers has a specific capacity to absorb the heavy metals, and the heavy metals is the one which makes the dye darker. So which absorbs the heavy metals and then releases the organics for us, because the nanofibers cannot reduce organics. It releases heavy metals. Once it releases heavy metals, it reads a lighter color. That lighter color is easier for the light to penetrate for our optical systems. Appo we kick on photocatalysis to reduce the organics completely. Appo enna aguduna ungalku in the absorption catalysis will help to reduce the organic radicals and give you a clean water, so that we reduce the toxic water or toxic water and then non-toxic water. That is the concept which we are developing. I hope it is.
Thank you, sir. Your talk is interesting and gives us an insight based on management and various technologies used for the purification of water and energy harvesting. Also, explain the various technologies used for the analysis of 2D materials and the photocatalytic process. Thank you, sir. In spite of the busy schedule, you accepted our invitation and give us an illuminating presentation. On behalf of the organizing committee of this conference, I thank you, sir.
I have a couple of questions in the chat which I would like to address. Somebody called RGV, they have asked, please explain about Maxine, and did you find Maxine or good for thermoelectric energy conversion? Okay, Maxine is another form of 2D materials. 2D, I already explained what is 2D systems. So where Maxine is produced, Maxine வந்து கிட்டத்தட்ட ஒரு 250 varieties or something more than that is there, different combinations. So we produce Maxine using our hydrothermal methods. Okay, and in that particular that is the extraction of layers. Okay, with M gardu vandu metal, and then Xc gardu vandu it's a alkene properties. Okay, adula vandu you find, yeah, it is good thermoelectric energy conversion as well, because of the surface termination groups la vandu you can induce different electronic properties. And the different electronic and electrical properties la vandu you can have a whole career injections kondralam. So maybe I will write my email to you. Maybe I can send you some materials if you want to have some concrete reading. So I have sent you an email, my email to you, okay, which I have done. Okay, thank you, RGV. If any other questions from students or anything, I have a few more minutes I can spend.
Thank you, sir, for your wonderful presentation. So, do you want to interact with the students?
Oh, it's okay, பரவாயில்லைங்க. If there is a students கொஞ்சம் குவைட்டா இருக்காங்க, ரொம்ப இதுவா இருக்காங்கன்னு நினைக்கிறேன். But they can always be more expressive. You question உள்ள வச்சுக்காதீங்க, வெளியில கொண்டு வந்துருங்க. That is what that will help us to understand whether நானே கொஞ்சம் வளர்னாலும் வளரி இருப்பேன். So but you can correct me as well if there is any opportunity.
Okay, sir. Thank you, sir. Thank you for your wonderful presentation. Have a great day, sir. Thank you.
Thank you so much. Have a nice day and stay safe. Okay, bye. Thank you. Bye.
Okay, the last invited talk for this today's international conference by Dr. G. Ravi. He is the professor and associate professor at the Department of Physics at Adappa University, College. So now I take the privilege to welcome Dr. R. Ravi to introduce Dr. G. Ravi. Good afternoon to everyone. Good afternoon to everyone. It's my great pleasure to introduce Professor Dr. G. Ravi, Professor and Head, Department of Physics, Adappa University, College. Sir has got a MPhil and PhD degree from Chennai. Professor G. Ravi was postdoctoral fellow at National Institute of Material Science, Japan. Professor G. Ravi has been received more than 10 awards and research fellowship various research fields and various countries. Professor G. Ravi various research fields, industry in personal growth and organic and inorganic material, moderator, organic and inorganic material and optical memory devices, nanostructures, then for sensor applications. He has completed successfully more than 5 projects funded by AST, DST, UGC, and currently ongoing projects in DST, SEL, UGC, SAB, DST FIST coordinator, DST first, department coordinator, MHRD. Professor C. Ravi developed his research laboratory in Adappa University for the laboratory of low temperature solution growth lab and film laboratory, sputtering, electron beam evaporation, spin coating, surface research facility developed in Nalapa University instrumentation lab for FTIR, gas sensor, spectrometer, electrochemical oxidation, thermal analysis, solar instrumentation. Sarkas guided in previously 18, 14, 49 young scholars, MSc 56 student, and ongoing researchers doing in PDF 2 members, PhD, three scholars, MSc in four students. Professor G. Ravi has published national and international journal in 370 papers, national and international journal conference published papers in 309. Sarkas published in 4 book chapters. Got received in 5 papers at various fields. Sarkas delivered in 42 lectures in various international and national conferences and 23 countries visited in abroad, 22 conferences and seminars also been organized by various Alabama University, Sarkas memberships in academic bodies in Indian Association President of the Research Society India, Japan Society for Promotion of Science and other organizations. I invite Professor Dr. G. Ravi to deliver your presentation.
So good afternoon to everyone of you. So I feel so happy to be here to present my work, part of my work on perovskite solar cells. So first of all, I would like to thank the organizers, particularly Professor Prem, for inviting me to deliver this lecture. So thank you very much for the nice introduction. So it's a very elaborate introduction given me. So actually, as he pointed out, I am from Alabama University, Karakudi. I joined in Alabama University in the year 1995 as a lecturer after my PhD at Anna University, Chennai. So as far as Alabama University is concerned, Alabama University is the A+ graded university. In the third cycle, the Alabama University has got 3.64 score in 2017. So Alabama University has got a very wide range of disciplines. So mostly the interdisciplinary programs are being conducted in Alabama University. So as far as my department, this department is concerned, the department has established in the year 1985. Then for the last 37 years, the department has produced 1,400 research articles in 90 international journals. And after I assume, after I take over charge as head, the incidence of the department has improved from 48 to 65. So these achievements is not because of me. So all the faculty members who are involved in research in Department of Physics. So before going to my topic, I would like to say something about my university. So Alabama University, the galaxy of institutions are established by this gentleman, Dr. Radhappa Chettiar. So actually, Dr. Radhappa Chettiar, he was a businessman. He started his educational service at his age of 38. He died at his age of 48. Just to imagine, just within 3 years, he would be able to establish, start from Montessori school, Adapa Preparatory School, Adapa, there is what do you call, Adapa Engineering College, Adapa Polytechnic, Adapa Model School, then Adapa Arts and Science College, Adapa College of Education, Adapa College of Physical Education, then Central Electronic Research Institute, which comes under CSIR now. So all those institutions were established by himself. So he wanted to bring all the downtrodden people of the whole district. He wanted to educate all the people. He spent all his money for education. So he has donated nearly 1,000 acres of land to the government. So at present cost, it's about 20,000 crore rupees. So he is such a very great person. He was a philanthropist, and he was properly called by. He used to call by our Prime Minister Jawaharlal Nehru. Dr. is social economist. So that's the correct word coined by Jawaharlal Nehru. So I take this opportunity to pay my tribute to Dr. And in my department, we are working in 3 fields. So crystal growth, thin film, and then solid state ions. So I am basically a crystal grower. So I started my career with crystal growth research. So I started my research in 1990 at Anna University, Chennai. Of course, your alumni. He was the director. Who was your alumni? Professor P. Ramasamy. So he established a center, Crystal Growth Center at Anna University. So I had a chance to work under him. So at that time, he always insisted to grow large size crystal. So nowadays, people, if you ask any person who is doing work on crystal growth, he used to grow very, very small crystals and characterize them and publish some papers, read their PhD, that's all. So during 90s itself, Professor P. Ramasamy, he was very much, he had a very good vision to have a crystal and to make the devices. So in that aspect, I had been working on growing KDP and DKDP crystal. Though KDP and DKDP crystals are very old crystal, he was insisting me to grow very large crystal. So I could be able to grow 20 centimeter length and 5 centimeter by 5 centimeter dimension of KDP and DKDP crystal at that time. So for growing crystal, we need a great patience. So unless otherwise having the patience, the crystal won't grow. So of course, I have spent 3 years for growing the crystals. So I had no publication. So till 1993. But Professor Ramasamy said, so let's do the crystal and you make some device to finish your PhD. But at that time also, when I finished my PhD, I have to have some publication for my PhD. So parallelly, what I did, I have known some crystals like TGS, LRGN phosphate. So without his knowledge, so I put some dopants and I include this LAP and TGS crystal parallelly. So after growing the crystal, I was instructed to go to Udaipur Solar Observatory, where one giant telescope is there. That is ISA Observatory. They need electronic modulator. They need electronic modulator at the time. So electronic modulator has to make through the KDP and DKDP crystal. So I went there. At the time I was I don't know anything. So I stayed in for three months, and I identify the orientation. There are so many studies I have done that. Then after making polishing itself is a great technology. Polishing, crystal polishing. So I spent nearly 2 months to polish our crystal, and at first I made the electron modulator, and then the electron modulator was housed in the giant telescope, and that electron modulator was used to find out some studies on the sun. So sun's activity, particularly how much radiation coming out from the sun, and what is the effect taking place in the atmosphere. There are so many studies that are going on there. So our crystal was working very well, so I was so happy. So apparently I gave to some doctors, Then at the time he contacted me, Professor Ramaswamy, Ravi, you have finished your work, then when you are planning to come to Chennai, Madras at the time. Then I said, so I have some work at IIT Delhi. So what do you have at IIT Delhi? I said, I do some more crystals. So I want to study the crystals in IIT Delhi. Then he said, how do you grow crystals without my knowledge? He said. He politely asked. Then I said, so I grew some crystals for my publication. He said, okay, you go and do some studies at IIT Delhi. If you want to know any person in IIT Delhi, I will introduce you. So that kind of conversation he has made. And I did some measurement for 2 months, and after we come back to Chennai, I could able to publish 7 papers on KDP, not KDP, on the So I couldn't even publish a single paper on KDP. But the publication, so the later stage I found that the publication can be useful only for applying PDF or getting job. But the real satisfaction only comes with making some device, useful device. The same electronic modulator I used in optical communication. So audio and video communications, we have made the modulator. Then it was performing very well, even by having this helium analyzer. We could transmit the audio as well as any distance through electronic modulator. So that was performing very well at the I think electronics and communication department at the university. So that was my work, and then after joining Alabama University, I had a chance to have a collaboration with them. So with the collaboration, I could grow some crystals of lithium niobate. So lithium niobate, the purpose of growing lithium niobate and lithium niobate was to make optical memory devices. So nowadays we are using the pen drives, which is USB, with a maximum capacity of some 30 GB or 40 GB. That is the maximum we can get through the pen drive or USB. But if you use a crystal like lithium niobate or lithium niobate, so we can store continuously 3 to 5 terabits. So it's about 3000 GB to 5000 GB. So that much of capacity we can that much of capacity material can be stored in a 1 centimeter cube of a lithium niobate crystal. So in that aspect we have succeeded, and moreover the information which is being stored in the crystal and the information which is being retrieved is so fast. So there is a 5 GB per second unimaginable speed. So nowadays we can have the speed of so what's the maximum speed one can get in the computer or using pen drive? Can anyone say? எவ்வளவு கிடைக்கும்? மேக்ஸிமம் 100 MB தான் பண்ண முடியும். மேக்ஸிமம் 100 MB. ஸோ நீங்க ஸ்டோர் பண்றதுக்கும் எடுக்கிறதுக்கும் 100 MB தான் பண்ணணும். But at the same time, when you use the lithium niobate crystal, you can go up to 5 GB per second. So that much fast is possible. The only thing is the stability, lifetime. So if you store the information, you can store the information intactly, so only for some 6 months to 1 year. So that is the maximum. So in that aspect, I have made some research. So doping. So doping matters in lithium niobate. So by doping lithium matters, so we were able to increase the stability. So maximum 3 years we could wait. So we had I had a collaborative with companies in Japan. It's a pioneer. So where they studied after the crystal, that is a managed lithium crystal, and they got 5 TB, that is the storage capacity, and the storage speed was 5 GB per second, and the lifetime, that is the stability, was 3 years. But still the research is going on. So if we achieve the stability of 10 years, then that will definitely come into the market. So the kind of research is still going on. So that is my second part. That is the third part. We could able to make some films like WO3, MO3 based films for gas sensors. So we made some gas sensors for sensing ammonia and carbon monoxide. So in that aspect, we had succeeded, and we could publish some good quality articles in international journal. So that is the third part of my research. So today my presentation will be focused on the perovskite solar cell. So perovskite solar cell. So go to the next slide. So this is the outline of so energy crisis and environmental. So energy crisis and environmental pollution. So nowadays when you talk about the environmental pollution, that is global warming. So you know the reason. Actually, the previous speaker, he reduced my job. So he gave the internal the physical meaning of how the charges being transported in the photocatalysis. So the energy crisis means we are using fossil fuel. Okay, so petroleum related fuel we are using. So that is getting depleted. So in another 20 to 30 years, you won't get the petroleum product. That is the fossil fuels is getting depleted. So that is one of the major issue. And then the second issue is the environmental pollution. So if you use continuously this fossil fuel, that will contaminate our planet. So ours is the only planet is having the potential to feed the human. So none other Earth, so no one has to find the planet which is suitable to live. So we are totally spoiling our Earth. So by using the fossil fuel, so when you are continuously using fossil fuel, then will emit carbon dioxide. So nitrogen more. So that kind of pollution definitely reduce the that is the lifetime of our Earth. So this is the second issue. So we have to find out the alternate energy source. So alternate energy source means there is an alternate, that is the renewable energy sources. So renewable energy sources, we know we can get energy by different means, by wind, by hydro, or by solar. So solar energy, solar cell, that is today's focus. So in solar cells, we have different solar cells, and my focus will be on perovskite solar cell. So I'll tell you what is perovskite solar cell. And in perovskite solar cell, we can have different layers. First one is the TCO, that is a transparent conducting oxide layer, it's the first layer. Then the second layer will be the ETL. that is the electron transport layer. Then the third layer will be the perovskite layer. Then the fourth layer will be the HTF, whole transport layer, HTF. Then fifth one is the contact. So we are using the whole as the contact layer. So the 5 layers that constitutes the perovskite solar cell. So actually, my research work in perovskite solar cell is the ET layer, electron transport layer, using tin oxide, and then some doping to improve the efficiency of the solar cell. Next slide. So this slide clearly indicates how much the world population is. So this is the state of the climate. Actually, you can see many of the places in the globe is the hottest climate, and some places is very cold. So it is deviating from the normal condition, and this will end up with global warming. So unpredicted rain, unpredicted drought. So there are so many issues. So next slide. So this is the energy demand. So actually, we are getting energy through different sources like nuclear and then the renewable energy sources. So the nuclear is not official due to radiation, and then the renewable energy. So there is a steam using renewable energy. And petroleum we are still using more and more. But the coal, this is the coal is coming out. And the second part you can see, this is the pollution level. So actually in 2060, the carbon emission of pollution was there is 310 how that is to further continuing. So this much of pollution is taking in our air. And here you can see this part. So this is the whole scenario. Of course, the natural gas nearly 30% natural gas. Petroleum and would only make 80%, almost 30%, and renewable. So, we have to use the solar, wind, biomass, where we So this is the whole energy. So I think the solar, the sun, the zero energy but the world energy consumption per year is 16 hours. So this is the total reserve available in the world and the demand. Next. So this is the solar energy is one of the main area. So what is the carrying on and all to be on. So actually the solar is very deep and inexhaustible and is currently available in our planet compared to the other energy sources. So the sun has a total energy of 2.34 joules per day. The world energy requirement in the whole year. So the photovoltaic result is global. So actually the year 1999 from the solar, the maximum conversion efficiency of the solar cell was 4 to 6%. Then after 1989, intensive research is going on so that we will be able to get a maximum conversion efficiency of 43%. So this is the basic diagram of the solar cell. So you can have a village and solar cell. That is the village of the and when we are explaining this engine, so you can have a development mode as a training. Then you can enter the external law. I mean, very long in this case. So as well as the solar cell is four parameters are very important. The first one is the power of the design. Four parameters. So this is the classification of solar cell. We have the first generation, second generation, and third generation solar cell. The first generation solar cells introduce the silicon energy solar cell. So silicon, we have either a silicon or so silicon making the but at the same time, the maximum usage would continue to the but the last result is more. So the people prefer to find these products this is the first generation solar cell. And the second generation solar cell is the Indian phosphate and supplements like agricultural grade, GAPA. So these are more that we use and the third generation technology is non-organic. So in this category, we have the so this is okay. So just if you see this slide, you will understand the importance of the renewable energy. So after 2010, there is a very key trend in utilizing the renewable energy sources. So here you can see this is the renewable energy source part. Next slide. Next. So perovskite, actually the perovskite is nothing but the structure. So it was proposed in century, the calcium titan, CaTA both. So that was the first material invented by scientists. Then afterwards, that name, that is a peroxide, is a Russian scientist. He was named after this solar cell. But the basic structure, there you can see the tolerance factor and the octave. So these two factors are most important. So the tolerance factor, there should be in between 0.8 and 1.11. And similarly, octahedral factor, there should be between 0.44 and 0.9. Suppose if we have these two factors range in this value, then we can conveniently utilize that material for the perovskite solar cell. So this is the architecture of the perovskite solar cell. We can have different types of perovskite solar cells. So planar structure, NIP structure, PNP structure, and similarly we can have the mesopore structure of PAP and NIP structure, and ETL free configuration, the STM free configuration. These are some of the architectures of the perovskite solar cell. Next slide. So this slide clearly shows the working mechanism of the perovskite solar cell. So here you see the TCO, and then ETL, electron transport layer, then perovskite layer, then HTL, then metal contact. So all this makes the perovskite solar cell. So when the light falls on the perovskite layer, then there is a charge separation, electron-hole separation. So the electrons will move upward and holes will move downward. When there is a proper matching between the perovskite layer and the ETL, then the charge will be, these electrons will be transported from perovskite to the ETL layer. And similarly, if there is a proper matching, there is a valence band matching between the HTL and perovskite, then the hole will be transported. So if you connect to the outer circuit, then there will be a recombination. So this perovskite solar cell will function perfectly. In my part, initially we tried with the ETL free perovskite. We have ETL free perovskite solar cell. So in the ETL free means we have to use the TCO layer. This transparent conducting oxide layer. We use that material, that is cadmium oxide, neodymium to CDO, cadmium tin oxide, cadmium zinc oxide. So these materials we prefer as the TCO layer, and then the active layer, that is the conventional material of that is a triple perovskite. Then HTA layer was the spiral OEM. So that is an organic material which has been used to make the HTA layer, and the contact layer was gold. So this is the architecture of the ETL free perovskite. Next. So actually for making TCO, so if you want to have a CDO based TCO material, so we have to use the sputtering technique, sputtering method. So sputtering method, we have to have a organic material of either cadmium oxide or n-doped cadmium oxide. So this is the target. So when you are bombarding the target with the argon ion, then the bombarded argon material will go to the substrate. So the substrate is placed at the top. Then the layer, the formation occurs on the substrate. So this is the equipment used for making the thin film of cadmium oxide. Next. So this is the experimental condition. So the target, these four materials we have used as the target, and the substrate was glass. The target to substrate distance was centimeters. Substrate temperature, room temperature, sputtering power. So we are varying this number as sputtering power 100 watt to 200 watt. Sputtering gas was argon. and then the base pressure was the 2 into 10 power minus 3 bar. Working pressure has been reduced from the base pressure level of 2.10 2 into 10 power minus 6 3 into 10 power minus 6 minus 3 millibar. And then the deposition time, the optimized deposition time was 30 minutes. Next. So for the perovskite air preparation, so that is the recipe. So different material we have to use for the preparation of the perovskite layer. So these are all some lead iodide, formamide, lead bromide, methylamine bromide. So these are all some of the materials that have been used to make the perovskite layer. So actually after making the solution, we have used the spin coating to have the proper thinking of perovskite. So spin coating we have to adopt certain conditions. Otherwise, we won't get a proper thinking of perovskite layer. Next slide. So this is the HCl preparation. So again, the system of HCl. Materials. That is the deposition condition. So again, we use the spin coating method for the preparation of HCl. Next. So these are all some of the devices, perovskite devices we have made. And then top contact was made with the gold. So this is the top contact. So here you can see the base is the glass. This is the electric, and that is ECO, not the ETL, no ETL, ECO, and then perovskite, for which the HCl is deposited, and then this is the contact. So by this way, we have developed this perovskite solar cell. Next. So after making the perovskite solar cell, we have to find out the VOC, JAC, fill factor, and the PC, that is the photon conversion efficiency. So in this slide, you can clearly see the effect of doping and the composition of the material. Cadmium oxide, we got VOC of 0.88 and JAC of 8.01 and fill factor 46.01, and this is the final photon conversion efficiency, that is 3.28. But when we are doping cadmium oxide to neodymium, this value has been improved to 5.31. 5.31, but at the same time, cadmium dioxide that reduced the PC value to 2.18. But at the same time, the cadmium oxide zinc oxide, this value has been improved to 8.2. Okay, so this is the first part of my. I have not plus 8.2 is not much. So in that case, so I want to make ETL. So this is and the next step we want to bring the ETL. The electron transport layer. So these are some of the ideal characteristics of the ETL layer. Good output transparency, good electrical conductivity, large electron mobility, low temperature process stability. So these are all important ideal characteristics of the ETL layer. So previously people used titanium oxide as the ETL layer. So when you use the titanium oxide as the ETL layer, structure, we could able to get the efficiency of 23%. But at the same time, the stability of perovskite solar cell based on titanium oxide based ETL layer will not be sufficient. So even if we keep all the properties getting depleted. So next slide. So that's what we preferred by using the tin oxide, not the titanium oxide. So when we use the tin oxide instead of titanium oxide, this These are some advantageous properties. So wide band gap, deep conduction band and high transparency, high electron mobility, then the large electron extraction and uniform crystalline grain. So these are some of the advantageous properties as compared to titanium SPT. So you use the pure tin oxide. So again, you can improve the efficiency of the solar cell by doping or using the right method of forming the EDL layer. So either you can use the auto sputtering or atomic layer deposition or spin coating. So in this, we used the spin coating method, so that gave us a very good result. And doping, we have chosen two different dopants, platinum and aluminum. So the reason is, when you use the aluminum as a dopant, it improves the transmission percentage. The transmission percentage is most important. Once you have a good transmission percentage, then the electron transport will be easier. And while using lanthanum, it will give the uniform deposition. So pin hole free tin film. So that is the most importantly needed. So if you use the titanium oxide as the interior layer, so we can find so much of pin holes. So that could be avoided using property in oxide. Here, TCO. TCO layer as a F2, is a fluorine tin oxide, and ETL layer pure tin oxide, and aluminum lanthanum separately doped. There is tin oxide and photo. So more materials we have prepared, and then the active layer was the triple cation perovskite. So that is another thing. We have not recipe of this perovskite layer, and HDL, that is the spiral OME layer. So we didn't get that part also. Then the contact layer was gold. So we changed only the HDL layer, this pure tin oxide, aluminum and lanthanum separately gold. So this is the fabrication process. So here you can see the ETL solution, how to make the ETL, make the ETL layer, and then look at that process. So here is the OMED tag, that is the HCl layer. So all three parts is prepared by the spin coater. So we have to keep the spin coater inside the glow box. And then the contact, gold contact. So gold contact was made with the electron oxide. So this is most important because the thickness of each and every layer is most important. Actually, ETL, we optimized 100 nanometer, and then the perovskite layer was 430 nanometer, and then HDL was 220 nanometer, and then the gold contact was 80 nanometer. It's the optimized values of the thickness of the different layers. Next. So we have to do many characterization activities. Through XPS, we can find out the presence of tin, aluminum, and lanthanum. And similarly, the X-ray spectra of this material. This is the same images. So in this same images, it is clearly indicated that the aluminum lanthanum co-doped tin oxide is having that is a pinhole free, and moreover, the grain size is more when compared to this and this. So pure tin oxide, so we can have a bigger grain size. important. Unless otherwise having a pinhole free layer, so we cannot expect any conversion efficiency. Next. So that is the transition principle of pure tin oxide and aluminum tin oxide. Yeah. So from this we can calculate the band gap energy. So if we calculate energy for pure tin oxide, that is 3.76. That has been improved further to 3.9 for aluminum lanthanum mode of the fan. So once you have the larger band gap, we can have a more energy conversion. And similarly, this is called this UPS, ultraviolet photoelectron spectroscopy. So from this we can find out the conduction band potential energy as well as the valence band potential energy. So if you know these two potential energies, then we will know how compact the ET layer is the perovskite layer. So this is also most important. This determining the potential energy of the valence band and then conducting band. Next. So this slide, this is for pure tin oxide, and initially we tried with aluminum doped tin oxide with the different composites, 0.5, 1 and 1.5. So in this, we got a very good result for the 1% aluminum doped tin oxide. It's 18.36%. This is the final PC value. Then VOC, JAC, fill factor, all the values are given here. And similarly, this is for the lanthanum doped tin oxide. So in this, the 1% lanthanum doped tin oxide that will give us a very good result of 18.21%. Next. So this is for aluminum lanthanum doped tin oxide. Here you see for the pure tin oxide, the PC value is 17.21, whereas the aluminum lanthanum doped tin oxide that gave us 19.13%. So this is very, very important result. Actually, you can ask me, so what's the difference between this only percentage? How the 2% makes great impact? But even if you change the 0.1% of conversion efficiency, that is a really good result. So in our case, we got nearly 2% more in the case of aluminum doped tin oxide as a ET layer. Next. So that one is the PL, photoluminescence measurement. Here you can see this intensity is getting reduced. There is a punching of the light intensity. So this is very, very, very important. Actually, the punching is the most important. Why? Because this when you reduce the intensity, that indicates how far your ET layer is being present. So suppose if the ET layer is defect free, then the punching will be more. It is a much reduction in the intensity of it. So in our case, that is aluminum lanthanum tin oxide, we got almost zero intensity. Okay, so that indicates your ET layer is 100% covered. And this is the EAS, that is impedance spectroscopic analysis. So at the high frequency region, this is at the mid frequency region. So this will give you the resistance occurred in your material ETA. Suppose at high frequency region, if you have a less semicircle, that means the series resistance of your ET layer will be less. And at the mid frequency region, if we have this kind of pattern, that means the recombination resistance is more. So recombination resistance would be high. At the same time, the series resistance would be low. So recombination resistance more means once the electron and hole pairs are generated, then they should not recombine each other at the initial stage. So in the external circuit, there can recombine, but internally there should not be any recombination. So at that case, the recombination resistance will be more.
Sir, but the pole for both the cases.
Pattern வந்து சேம் தான், பட் வந்து உங்களுக்கு வந்து இந்த செமி சர்க்கிளோட அது வந்து ரெடியூஸ் ஆகிடும். ஸோ இது ரெடியூஸ் ஆகுது அப்படின்னாலே உங்களுக்கு சீரிஸ் ரெசிஸ்டன்ஸ் வந்து குறையுது. அதே நேரத்தில் இந்த இதுதான் மிடில் ஃப்ரீக்வன்சி ரீஜன். மிடில் ஃப்ரீக்வன்சி ரீஜன்ல வந்து ரீகாம்பினேஷன் ரெசிஸ்டன்ஸ் அதிகமாக இருக்கிறது தான். அது என்னன்னா அந்த மெயினாக பார்த்தீங்க அப்படின்னா இந்த டைஎலக்ட்ரிக் கெப்பாசிட்டன்ஸ் அண்ட் கெப்பாசிட்டிவ் எலமெண்ட். ஸோ from this we can directly find out the series resistance and the recombinant resistance. Actually, these are all the values we obtained for this tin oxide ETL and aluminum and tin oxide ETL. So you see the series resistance for tin oxide, that is 16.1, aluminum and tin oxide, that is 14.9, and similarly the recombinant resistance is 2.59, whereas the code of the sample, that is a 10.3. So it's a very remarkable value we got. Next slide. So this is the reproducibility analysis. So we have not done only with the single sample. So we have prepared 20 perovskite solar cell in each category. Pure tin oxide. Then this one is aluminum tin oxide and lateral tin oxide. So 20 devices we have checked for VOC, JSC, fill factor and PC. So from this we can clearly say that the aluminum lanthanum photo tin oxide ETL, the average PC value of 18.4%, whereas the tin oxide, the average PC value is 16.28. Next slide. The stability, as I already said, the stability is a very important criteria as far as the perovskite solar cell is concerned. Actually, we kept our devices in the open atmosphere with the humidity of 40% for 30 days. So for 30 days, so the device that retained 80% of its initial PCB in the case of tin oxide based ETL, whereas aluminum lanthanum photo, that is 90% is retained after 30 days. Even if you keep it at room temperature or with the humidity of 30%, that will be very safe. Next. This is the photo stability. Again, photo stability we have found out for this sample. So among this photo of the ETL that exhibit a very good value. The photo stability was very good. Next. Okay, so from all those studies, we can conclude that the code of the ETL that is very much suitable for making the perovskite solar cell. So the reason for the improvement of the photoconversion efficiency, as I already pointed out, so this is mainly because of the higher transparency and the smooth surface of the aluminum lanthanum photo sample. So that is a defect-free layer. So these are the main reasons for the improvement of the photoconversion efficiency of this perovskite solar cell. So thank you very much.
Thank you, sir. So this talk is open for discussion. So if you do have any question, you can post the question to the resource person. 1 or 2 questions. Faster, timer. You should go for presentation. Then 1 or 2 questions தான் கேட்கலாம். மேடம்.
actually SM based அப்படின்னு சொல்லும்போது easily oxidized அப்படின்னு சொல்லுவாங்க. ஸோ அப்போ வந்து அதோட ஸ்டெபிலிட்டி கம்மி அப்படிங்கிறதுனால பெரோஸ்கைட் வந்து அதை யூஸ் பண்ண மாட்டோம்னு சொல்லிட்டு.
எதுங்க டின் ஆக்சைடு?
இல்ல SM நம்ம இதை இதுல யூஸ் பண்ணுறோம்ல.
இல்ல இப்போ டின் ஆக்சைடு லேயர் நம்ம யூஸ் பண்றோம் அப்படின்னா டின் ஆக்சைடு அந்த ஆக்சிடேஷன் இஸ் நாட் a problem. ஏன்னா நீங்க டின்னா யூஸ் பண்ணல, டின் ஆக்சைடா தான் யூஸ் பண்ணுங்க. டின் ஆக்சைடா யூஸ் பண்ணும்போது உங்களுக்கு ஆக்சிடேஷன் இஷ்யூ வராது, சரிங்களா? அதே நேரத்தில் டைட்டானியம் ஆக்சைடு யூஸ் பண்ணீங்க அப்படின்னா there is some issues. ஏன்னா இது வரைக்கும் பெரோஸ்கைட் சோலார் செல்ஸ் எல்லாமே டைட்டானியம் ஆக்சைடு பெரோஸ்கைட் தான் பண்ணியிருக்காங்க. அது பண்ணும்போது பாத்தீங்கன்னா எஃபிஷியன்சி showing nearly 22%, 22.1% in the latest for 2 months back வந்து அவங்க சொல்லி ரிப்போர்ட் பண்ணிருக்காங்க. பட் அதோட ஸ்டெபிலிட்டி அதனால தான் அந்த இஷ்யூ வருது. Even though it exhibits 22.1% of efficiency, but the stability is very poor. அதை வந்து நம்ம இம்ப்ரூவ் பண்றதுக்கு தான் என்ன எப்படி அப்படின்னு நம்ம டின் ஆக்சைடு பேஸ்ட் மெட்டீரியல் tin oxide based material போகும்போது we can have a larger band gap. Tin oxide based வந்து we can have a 3.7 electron. Even if you further improve the band gap, that would be good for the perovskite solar cell. So நம்ம கேஸுக்கு வந்து அலுமினியம் நேச்சுரல் கோட் ஓபன் பண்ணும்போது 3.64 ல இருந்து 3.9 போகும். So that is an advantageous factor.
Thank you.
Actually, a simple question only. So you have obtained the values for INP, so voltage versus current. So from which instrument you get this values?
Actually, you have to have the solar simulator.
Okay.
So solar simulator அப்படின்னு பார்க்கும்போது யூஸ் பண்றது xenon lamp யூஸ் பண்ணுங்க. அதுக்கு வந்து நீங்க அந்த வேல்யூஸ் எடுத்து எலக்ட்ரோமீட்டர் யூஸ் பண்ணுங்க.
Electrometer source.
So source வந்து உங்களுக்கு வந்து xenon lamp. So source வந்து xenon lamp. அது வந்து you have to match with the sunlight. அந்த இதுக்கு அந்த மாதிரி நீங்க மேட்ச் பண்ணணும். ஸோ அப்பதான் நீங்க வந்து கரெக்டாக அந்த கன்வெர்ட் சொல்ல முடியும். அது அந்த கால்குலேஷன் நீங்க பண்ணலாம்.
காஸ்ட் எவ்வளவு சார்?
எதுக்கு
இந்த மாதிரி நம்ம
கிட்டத்தட்ட உங்களுக்கு வந்து 30 lakhs.
30 lakhs.
ஆமா 30 lakhs. ஸோ உங்களுக்கு you want to have a good solar simulator, at least 30 lakhs.
சார் கொலாபரேஷன் ஏதாவது இங்க சில பேர் பண்றாங்க. ஸோ அவங்க உங்க லேப்ல வந்து ஏதாவது பண்றது
நீங்க வந்து நீங்க பண்ணலாம். ஈவன் அந்த பேமெண்ட் பேசிஸ். ஏன்னா எங்க லேப் பொறுத்த வரைக்கும் எவ்ரி ஃபார் ஆல் வித் மினிமம் சார்ஜ். ஸோ XRD we are charging only 400 rupees. But the result you can get it within 3 days or 4 days. அது ஒன்று. அது மாதிரி போட்டோ லுமினசன்ஸ் இருக்கு, ராமன் இருக்கு. ஸோ ராமன் we are charging only 600 rupees per sample. Solar simulator இருக்கு, CGDT இருக்கு. So you can go up to 1000 degrees. Thermal analysis, UV இருக்கு, FTA இருக்கு. So basic characterizations எல்லாம் thickness எல்லாமே. பட் அதே நேரத்தில் நீங்க XPS டிரான்ஸ்மிஷன் செம் இதெல்லாம் எடுக்கணும் அப்படின்னா நீங்க have a separate center, instrumentation center. ஸோ அவங்களுக்கு வந்து அவங்களுக்கு செப்பரேட்டாக இருக்காங்க. ஸோ அங்கே வந்து நீங்க வந்து சாம்பிள்ஸ்.
தேங்க்யூ சார். தேங்க்யூ.
Biological material, some places we can use biological material. For example, அதாவது physics department XRD, PL, Raman, FTR, UV, thermal simultaneous thermal analyzer, and then solar. So இதுக்கெல்லாம் வந்து we don't restrict biology. So any material we are calculating, but at the same time for the thermal analysis, so we are getting another. So some materials the early stage. We cannot compare.
Sir, I'm sir. Sorry. Thank you, sir. Thank you. Thank you, sir, for a wonderful presentation. May I now may I invite Dr. S.G. Regit, Assistant Professor of Physics in Xavier's College, to honor Dr. G. Ravi with a short notes. May I now request Dr. M. Jirina, coordinator of Shift 2 of MSc PG curriculum, to give away the mementos and certificates to honorable resource person. Thank you, sir. Thank you. So be ready for a paper presentation. So you can break for tea. Those who are there for a oral paper presentation, yeah, I'm lost. Dear participants, please listen to the announcement and please go to the first floor. I will read out the numbers. Shirley, Carmel Vigilaban, Mugambigai, Sivasaranya, Mohammed Mekum, Anandamina Gita, Gayatri, Surya Mohan, Shania, Abhisha. Go to the Ziba block first floor. Is it clear? All others be remain here. Please have a tea and come back. And one more announcement. So those who are there for poster presentation, it is displayed outside the Ziba block. So you can approach Dr. L. Antoni Silva for further clarifications.